Well, it looks like it's the top of the hour here. Welcome, everybody. My name is Alan Pendon, and I am from Electorant and will be your moderator today. Thank you for attending this exciting webinar on understanding OTDR-OLTS analysis to reduce truck rolls and retests with our speaker, Kevin Perez from EXFO. Hey, Kevin, how you doing?
I'm doing well, sir. I'm doing well. Thank you very much.
Wonderful, wonderful. All right, so a little bit, excuse me, a little bit about Kevin. Kevin has been with EXFO for 19 years and has been involved in the telecom industry for 30 years. Kevin started as a laborer in his early years and eventually transitioned to lay cable across the country. Then he worked as a splicer and tester for a tier 1 service provider, helping with new installations and disaster recovery. Kevin later became an operations technician, setting up and maintaining DS1 to 10G systems. And with his experience he has acquired in the field, Kevin delivers a unique perspective, which can be seen in his educational approach when he delivers expert content through webinars and seminars. And just a little bit about Electorant. We are the largest testing and technology services provider. We're a global company with over $1.1 billion in inventory. We have invested $100 million in new inventory and have 122,000 units in stock. We deliver to over 100 countries, sent from over 27 offices and inventory centers, and we have 600 test specialists for responsive customer first experience. And with that, I'll pass it over to you, Kevin.
Thank you very much, Alan. So let me go ahead and, all right, perfect.
Yep.
So, okay, perfect, good deal. All right, so I'm gonna go and get started. So as Alan mentioned, my name is Kevin Perez. I do work directly for EXFO, and I'm sure some of you have sat in on some of my sessions as I do a lot of these. And so when we sat down to discuss what we wanted to talk about, I've been talking a lot about OTDRs here lately, but quite frankly, it's still probably the most in-demand session that we talk about. We're laying quite a bit of fiber today. Many of us are working on very high-count fiber systems, 864, 1728s. We're seeing a lot of these things going to ground today. So the need for testing has exponentially gotten more and more. And so every year I say that this is the biggest year, and so I got to say that again. We are putting in quite a bit of fiber. So we have quite a bit to cover here today. So I'm going to start off with a little bit of fiber fundamentals. I always do that because that's really the core base that you need when you're talking about OTDRs. Because once we get into the actual setup of the OTDR, a lot of the expertise comes from the interpretation of the results, and a lot of that relies on the basic understanding of fiber. Then we'll talk about connector interfaces and those types of things. I talk a lot about connectors because that's one of the biggest issues that causes problems within our network today for new installation and for turnup. And so the critical parameters that we'll be looking at and measuring with the OTDR today are going to be insertion loss. So how much power am I losing going across the connector, across the splice, across the span of fiber, right? What does my placement look like? Do I have any pinches or compressions? Do I have any issues with, say, a loop being, too tight inside of a splice tray or something like that? As well as reflection, which is a huge one that I'll spend time on, which is one of the big critical parameters that an OTDR allows you to look at that, say, something like a standard power meter doesn't measure for you. And so these are the things that we're going to be covering here today. Really to put it into perspective, the importance of minimizing the amount of loss or reflection in your system. This is my favorite table to show here. And really the big takeaway here for this particular one is for every 3 dB of loss that we have in a system, so every 3 dB of loss that we have in a system, we lose 50% of our performance. We lose 50% of our performance. And that means if you have a span of fiber that's 3 dB of loss, you've already lost 50% of the original power that was leaving the transmitter. Add another 6, then you have another 50%. So 50% on top of 50%. Now we're down to 25% of the power. And then, of course, 10 dB, we're getting down to 10%. So you kind of see how this scales, right? So this is logarithmic, so it's really kind of a scale. If you look at some of these values up top here, most companies that I work with today are looking at splice loss typically between 0.1 and 0.2 on the average. So 0.1 and 0.2 on the average. A lot of the newer splicing machines, if they're set up and used appropriately, consistently get very low loss splices. But this is kind of the pass fail that we're seeing today. So one splice at 0.1 dB loses 2% of the power passing through it. And so imagine if you have 10 or 15 splices, how this value can start to add up. And most connectors are sitting around half a dB or better on average for a connector, which is just a little over 10% loss from one connector. So this is why it's really important to maintain a good quality system. Although 0.5 dB is good enough for pass fail for most companies, typical is 0.2, 0.3. So, trying to get the highest level of quality is really important. And using the OTDR is one way to characterize just the kind of quality of work that's being done out there. So that's something important to understand, and I talk about that. And so, the two, of the two biggest parameters we're looking at, attenuation or the loss of power is one of them. And there's really two ways that it happens. One is intrinsically. Intrinsically meaning this is the loss of the glass itself, of the fiber itself, through absorption and scattering. So as that laser, that signal travels across the fiber, a portion of it gets absorbed or scattered, and then we have loss. And for most standard single mode fiber, so like G.652 stuff, depending on the manufacturer, this will vary, but typically it's about 0.2 dB of loss per kilometer at 1550, right? So for every kilometer, we're losing about 0.2 dB of loss. Again, this will vary. There's ultra low loss glass and other types, but this is just kind of a generalized statement here. This is at 1550. For 1310, also depends. It's usually about 0.34 in that range of loss per kilometer at 1310. So 1310 nanometers has more attenuation. So that's one of the fiber basics that we need to understand, is that different wavelengths have different loss characteristics along the fiber, right? And so 1550 has less loss. So if we look at 100 kilometers of fiber, which is roughly 60 miles or so, it's 20 dB of loss at 1550 and around 34, 35 at 1310 of just the glass. So that gives you an idea of the huge difference. And as I mentioned in the scale before, for every 3 dB, we take a 50% hit. And so if you look at this, there is quite a bit of difference between the two, right? And so we are taking a pretty significant hit, of attenuation at the shorter wavelengths like 1310. So a lot of the legacy systems that we have today are 1310. So some of the troubleshooting we're talking about is to qualify fiber as you upgrade these legacy systems from 1310 to 1550 because you're deploying something like DWDM, right? So that's important to understand. The other big issue is extrinsic. So this is attenuation from outside influences, macro bends, splices, connectors, those types of things. These cause intrinsic loss that you have more control over. So this is where your splices are, 0.1 dB or better, depending on, whatever your threshold is, or connectors are 0.5 dB or better. So as the signal travels across these connectors, it's going to have some sort of a loss. And so this is what we call extrinsic losses. So think about the things in your network today that your signal passes through. It could be a MUX demux. It could be a CPRI interface device. There's a lot of different things out there like taps and splitters that introduce loss or attenuation into your system. And so the OTDR will help us measure that. To a large degree, most of the issues that I've dealt with as a technician were bad connectors. I analyze a lot of test data for a lot of customers today. I probably look at 10,000 traces a week. The ones that I do kick back, to a very large degree, most of them are because of a dirty connector. And most of those connectors are at the end of the launch cable or within the tie cable if you're testing through a building. to a very large degree, that's most of the stuff that I kick back, which is unfortunate because that's something that you can fix as a tester while you're on site. And by the time someone like me looks at it and says, "Oh man, it's that panel's dirty," or "There's something wrong there," we don't know, so it has to be retested, which means an additional truck roll. And to a very large degree, these are connectors. So when I talk about testing, I'm going to focus on validating your trace before you move on to the next fiber, because that's part of the reducing the truck roll stuff, right? So obviously we have losses from connectors. So this is primarily due to contamination or just not good connection. And so inspecting and cleaning is incredibly important. I'm not going to spend a lot of time on this, although it's one of the single most important things because of just, it really requires its own session. But having good cleaning practices, whatever type of device that you have. I'm a big fan of the hybrid method. Hybrid method being using some sort of a dry tissue. So whatever kind of dry tissue you have from whatever vendor, and then some sort of cleaning supply. So these are kind of the two big things that I look at. And when I'm cleaning, I essentially just wet a small portion of the dry tissue, start my connector in the wet and pull into the dry. I don't expose it to the atmosphere while it's wet, and I don't oversaturate it with too much solution. So those cause problems in themselves. And I cannot stress enough the importance of having good cleaning practice. So inspecting and cleaning your connectors. This is the biggest issue that we run into. So I did a video once. It's like a 15-minute video somewhere. I'm sure it's buried on YouTube. I know it's buried on YouTube. That I call cleaning connectors with an OTDR, which is basically troubleshooting contaminated or bad connectors using an OTDR. And we'll cover a portion of that here today. And then the other KPI, of course, is reflection, optical return loss and reflection, right? This is essentially noise in a system. What causes reflection? Most reflection, comes from change in material types. So going from fiber to air to fiber, and that happens mostly at connectors, right? Because you have a physical connection. That's what happens there. When you fuse a splice, you don't really have any high reflection. You have the reflection of the glass, but there's no air gap there. So, having these good connections and making sure that, you don't have this large air gap to minimize reflection is important. And so the two primary connector types that we have in the field today, UPC or ultra physical contact, and APC. So these are the two primary connectors. My background is more from the telco side. So a lot of it, from the telco and construction side, we lived and breathed flat polished connectors. So these are flat polished connectors, meaning where the fiber touches, it's flat. Right there, it's flat. The rest of this kind of rounds off a little bit, but the fiber itself is flat. So when you mate two of them together, it's kind of like that, right? So this is what we're looking at here. So this is a flat end face. So you can plug any flat end face into another flat end face as far as connectivity goes. APC connectors, angled physical contact. These have an 8-degree offset on there, and so they are angled. And the reason it's important to understand the difference between the two is because they do perform differently. So when you are testing, knowing the components that you have in your network and understanding, this is an old D4 connector. Well, that's going to be, there's a good possibility you're going to have higher reflection and loss because of the nature of that type of connector. This is an APC connector, so I expect to see better reflection. So the big difference between these two, spec-wise, they're both about 0.5 dB or better of attenuation at 1550. So power or loss-wise, it's about a half a dB for both of them for a mated pair. But reflection is completely different. Reflection on a UPC connector is about neg 55 dB, where the UPC connector is neg 65 dB. And this is the percentage of light that comes back. If I have an open flat connector, it is about neg 14.7 dB of reflection. That's an open UPC. As soon as I mate that UPC, it's going to hopefully jump up into the 50s. For UPC. For APC, it goes all the way up to minus 65. And remember, for every 3 dB, 50% difference. So it's 50% on top of 50% on top of 50% better. Much less reflection. We typically saw this in the video world. So a lot of the MSOs, anybody doing analog videos, submarine cables, heavy amplification, we saw APCs because those systems used a lot more power. And with more power, you have more issues with reflection or connectors. It's almost like pressure. I give this example all the time. If I take a garden hose and hold it up against the wall and crank the pressure up, it's a lot of power. It's going to hit the wall, which is the reflection, and then splash back into my face, which is noise. But as I decrease the pressure on the garden hose, it's going to hit the wall and run down the wall. I'm going to have much less splashback. So with APC connectors, because we had so much better reflection performance, these were used in heavily amplified systems like RF analog video. And so these are the two big connectors. You don't put these two together because there's been an evolution of connectors over the years. But most of them were all flat connectors. So going from, PC connectors to UPC connectors, all of these here were all flat. These are all flat end faces. They perform differently reflection-wise. So we're improving the reflection and the attenuation a little bit. And then we get the APC, which is all, by itself. It can only connect with other APC connectors. So this is important because if you don't have a good connection, what happens with fiber, if there's any sort of dark material that covers the core, so this part right here is the core. It's kind of hard to see, but this is the core right here, right? So this is the core, this is the cladding. And, a lot of folks think these are two different layers. They're not. They're actually adhered to each other and then melted together. So they're actually one big chunk of glass. And then you have the adhesive zone. So this is where we sometimes see a glue line. And then this is the portion that's flat all across here. Everything after this kind of rounds off. So this is the flat portion of a connector. So anything that lands here that, say, dark material will cause high loss, but not necessarily high reflection because it's absorbing light, not reflecting light. So you can have one without the other. If I have some large material here that's, say, 5, 6 microns and so, if it has any sort of a mass, it'll cause core separation, a larger air gap, higher reflection. So it is possible to have low loss and high reflection. It is possible to have high reflection and low loss. They don't necessarily have to, go together. So this is important to understand. For those of you that were technicians, I give this example all the time. When I got a call from the network operations center, said, Kevin, we're taking errors on this circuit pack, on this circuit. I would take my power meter, check the power levels at that circuit pack. And if it was, say, neg 15 dBm, well, that's good light for me in that situation. But I start cleaning all of my connectors inside of the building, at all the tie cables, at all the handoffs, at all the colo spaces. And I'm not trying to improve my power. I'm trying to improve my reflection. I'm trying to remove something that's causing a larger air gap or some kind of material that's reflective. And so an OTDR can help us troubleshoot which connector within the building to clean. And that's a big part of it, right? And so it is important to understand there are differences in how the wavelengths react. I mentioned earlier that 1550 is about 0.25 dB per kilometer, while 1310 is about 0.3 dB per kilometer. So we should have higher loss at splices and connectors at 1310 than 1550. If you ever see a situation where 1310 is better than the longer wavelength, then there is a good chance that we have a pinch in the fiber. So I like to show this. So for example, if I were to go in here to say an OTDR, wherever my OTDR is at here, there it is. So I got an OTDR here. So I did a shot. So if we look at, say, this connector right here, number 7, 0.10 at 1550, and it should be pretty similar at 1310. So 1310 is actually a tiny bit better, but they're fairly close. So in this situation here, I'm going to pinch it just to show. I like to show this, and if you sat into my seminars, you've probably seen me do this before, just to kind of show you how important it is to manage your fibers. So I'm going to grab a connection here. So I got a connector here, just a UPC connector. I'm gonna put a pinch in it. I'm going to put a pretty decent pinch in there. I know it's kind of hard to see. And then I'm going to retest it. So I'm going to retest it. I'll do a quick test at say 10 seconds here. Then we'll come back to the setup. We're still working on the 101 stuff, right? And so it's going to go through. It's going to shoot 1310 first. And hopefully I didn't pinch it too much. We'll see here in a second. I pinched it a lot. So you see, it dropped right there. but 1550 is going to be even worse. So 1550 probably. Oh, actually, the first one was 1550. This one's 1310. I read that wrong. So I did do a good pinch. So we're going to show what's happening here. So imagine the systems that you have today that are running 1310. You know, your short reach, 20 kilometer, 30 kilometer systems, single wavelength stuff, probably 1310. A lot of cell towers, backhaul, a lot of 1310. So as you increase your bandwidth going to 5G, going to 2, 6, 8 gig services to homes, all of a sudden the F2 side, the distribution side of it, all of a sudden needs more bandwidth, which part of that includes going to DWDM or increasing your spectral efficiency. That's getting you into the C-band, into the 1550 range. So your existing system right now, this is that connector. That connector right now at 1310 is 0.56 with a neg 47 dB of reflection. This should not be surface affecting at all. Should not be at all. It's just barely, actually for 1310, this is fine. And the reflection is fine for just about every system there. So this is a good connection. But now you go ahead and change the equipment on the ends, and now you have C-band stuff, you have DWDM, you're using bidirectional transceivers where one direction has a longer wavelength. If I switch this to 1550 now, that same connector is 4.3 dB of loss. So we gained over 4 dB of loss from that pinch in the fiber, but it only affected our longer wavelengths. This is critically important to understand. There's a lot of pinches in existing fiber out there, in existing raceways, existing splice traces that haven't been a huge issue because you're running an old FLM 2400 on it that's using 1310 nanometers. You know, when the world ends, it's going to be cockroaches and the FLM 2400 running at 1310. The things, they just work because they're low bandwidth, short wavelength, you know, equipment. And so now we need to troubleshoot this. This is not a bad connection. This is not a bad splice. I'm not going to go out there, expose the case, and break a splice and redo it. There's a fiber management issue somewhere. Could be a twist, a pinch, compression. Could be when you're bonding it and you take your nines and you hammer in your, you know, that, you know, your bond clamp into there and screw it down. Sometimes it'll push up against the ribbon. Things like that are things you have to look out for. And this is why it's important to understand the basics of fiber, because now we can tie this all in, right? We can tie this all in. So some of the things, some of the values that I mentioned, you know, from earlier, you know, for connectors, for most folks, we're looking at 0.5 dB or better at 1550. So I'm only going to use 1550 as a value here. There's a lot of companies that only do thresholds based on 1550. So we're looking at that. And then for splices, depending on your organization, somewhere between 0.1 to say 0.2 or 0.25, whatever, of loss at a splice. Reflection. For reflection, most companies are somewhere between as low as neg 40, which is a little low on the low side for me, to neg 50 or better, depending on the connector type. This is typically what we see. So these are common values that we see for pass-fail. Your own organization probably has their own. It could be tighter. It could be a little bit looser. It's important to know that there are these values, right? So knowing the limits is incredibly important. For span information, you can get from the OTDR, but it's better to get it from a continuous wave source. But for span, a lot of folks go with 0.25 dB per kilometer at 1550. And so this is the 0.2 for the fiber. And then, you know, if you move it up to 0.25, you have some margin to account for splices and connectors. Be careful with this value on short links. This number's skewed. It's like trying to get miles per gallon, but you drive 2 blocks, right? You need a little bit of distance to average that number down, because if you only have 1 kilometer of fiber and you have 4 splices, well, you're already well over 0.25 dB per kilometer, right? And then ORL, or optical return loss, this is what we call span reflection. So reflection itself is the individual percentage of light that returns from a single location. So this connector at 1.5 kilometers has neg 48.8 reflection, percentage of power bouncing off of that connector. ORL is the entire span, along with all the connectors and splices added up. This is a positive value. And most companies are between 27 to 32. 27 is an old OC192 spec, so I don't see that near as often. It's usually 28 or better. If you're from the video world, 32. 32 dB is what it was. So these are some of the values that we need to understand from the fundamental side of things, right? Because now when we look at the OTDR trace, we need to correlate some of this information. I'll come back how to set up the OTDR to make sure that we see this all, because that's incredibly important. But let's finish up the fiber fundamentals before we get to that part. So I'm going to look here. I didn't null out my launch cable, but I will during the next test. I like to do one test with no launch cable nulled out so I can measure what it is. And so in this case here, we see what the launch cable, it's 150 meters basically. So 0.1509. I'm going to go ahead and put that in there now, just because I have it, fresh in my mind. So in our OTDRs down here, I'll go to launch fiber. It's incredibly important to use a launch cable because we need to be able to separate our connection, our launch cable from, our OTDR port or IOLM port from the patch panel that we're testing. So this right here is actually my patch panel. When I retest, you'll see that that's what it is. If I go to the event table here, at my patch panel, I have 0.26 dB of loss here, and I have neg 54 dB of reflection. This is a UPC connector. I want a half a dB or better. I got that. I want somewhere between neg 40 and neg 50 or whatever based on your company. This one's, and I like to be around neg 50 myself. So this is above that, so I'm happy with that. Just after that, at 20 meters, we have another connection that's 0.43 dB of loss and neg 67, even better reflection. This is actually a UPC. So this here, an APC. This is a UPC at the panel. This is an APC on the backside. This is something you might see in something like a Centrex panel, where you might have something like an LC UPC on the front side of the FDP, and then the MPO on the backside is APC, and they're very close to each other. So this is something you might see in those types of situations. In this one here, this is just the stuff I have in my office. So as I scale across here, I'm just looking at everything. So I got a little bit of a gainer here. This is actually bend insensitive fiber here, this jumper. So I got a gainer from the bend insensitive fiber, then I got a loser on the other side. Reflection on both of them are great. See, this is important information to understand, because if this was the four walls of my site right here, there's the four walls of my site. Here's my vault splice outside. I want to make sure all of these are nice and clean, low reflection. I don't want to see anything that has a really tall peak. That's high reflection. Anything that goes up and then does this, ski slope, high reflection. I don't want to see anything that drops like a rock. I don't want to see 1310 better than 1550. So these are where the interpretation comes in. And now all of a sudden you start to understand, well, okay, the fiber fundamentals are a big part of the interpretation of running an OTDR. Because when I get to the setup, you'll see it's pretty easy. So that ties in kind of the fiber 101 stuff, right? Ties in understanding what causes attenuation and what some of the values should be and how to identify them on the event table. Now we need to get into some issues with the OTDR, which is basically kind of the OTDR theory portion of the presentation, right? And I'll go back to the deck for this because I really have some good slides on this. Normally I draw this out in the past, but I talked about the wavelength issues here. So I'm going to skip through a few of these probably because I talked about them and drew a little bit there. But an OTDR basically sends out a pulse of light. It's like a Doppler or radar, and it just interprets the backscatter. So pulses of light, that's a big thing here. And then backscatter. So there's the return stuff. So basically we use it to find a backhoe sticking up of our cable, right? That's one of the big uses of it for finding, a squirrel having lunch, dirty connectors, bad splices, bad fiber management, bad placement issues, just bad cable in general. It helps us identify those things if we have it set up correctly. And it's used by all groups during installation and construction, during maintenance, disaster recovery, requalifications, all of that stuff, right? It's really important that every stage of this understands how to test. Unfortunately, a lot of maintenance issues that I deal with when I was a tech was actually construction or installation issues that were never really fully vetted. And so it's turned over to me when I was on the operations side and I tried to put a circuit on it and I didn't test it. And all of a sudden we're taking errors. And if we gave it to a customer and all of a sudden the customer is opening a ticket for something that was already pre-existing, right? And OTDR can really help you qualify some of these issues. So all throughout the cycle of it, right? For looking at your splices and looking for a reflection. So light that bounces back. And I talked about this, the neg 14.7, dB. So, we'll give you a copy of this deck. That way you have all the nice fancy graphics and all the values that I scribbled down. But that's what we're doing, right? We're looking for all of this stuff. But to do it right, we have 3 primary settings. Range. So range is not how far you're testing, but how far you're seeing on the display. So when I set my range for 5 kilometers, it doesn't mean I'm testing 5 kilometers. I could be testing 10 kilometers. It's just going to show me 5 kilometers of the screen. And this trace could keep going right off the screen. Right? So this is the display range of the screen. So what you want to do here is you want to have, and you want to see most of the fiber fill up the screen, over 50% of it at least. I like closer to 75. I want to be able to see the end of the fiber, and I want to see the noise floor. And I want to clearly see the noise floor is there. I don't want to see something that comes down and then starts to get noisy, but it just keeps going off the screen, because there's a chance it just keeps going. It's just high loss is all that was. And you think you're seeing the end of fiber, but you're not. So it's important to clearly see the noise floor. Good OTDRs and good noise floors are 5 dB or below. And so that's the noise floor thing there. So that's setting number 1. Setting number 2 and 3 kind of go hand in hand. Pulse width, incredibly important. Well, they're all incredibly important. But pulse width is the length of the pulse in time. So a 5 nanosecond pulse width means the laser turns on for 5 nanoseconds and then turns off. It's about a meter or so. And so that's a very short pulse width. That's also our resolution, the size of our sampling. So the shorter our pulse width, the more we can see connectors and splices that are close together. So we get great resolution, but we can't test very far. So as I increase my pulse width, I increase my power so I can test further, but I start to blind myself to certain events. If there's 2 splices or 2 connectors that are close to each other and my pulse width is too long, it's going to merge them as one big event. And I'm going to show that here in a second. How we can offset this a little bit is with duration. Durations are averaging time. So only noise moves on an OTDR trace. So 4 times a second, we analyze for movement and smooth it out. So as I increase duration, I can decrease pulse width because I give it more time to clean up, right? And so, a good graphic of this is if I want better resolution, if I want to see 2 events that are close to each other, I need to crank my pulse width down and crank my duration up. And at 5 nanoseconds, I can clearly see I have 2 connectors here at 5 nanoseconds. But it's really, let me get my face out of the way here for a second. Sorry about that. I need to adjust this slide one day so my face isn't in the way. So let me move myself, get fancy, move myself up to the top here. So basically what happens here is you got great resolution up front, but you're really noisy on the end, so it's not very useful over here. So you see that? If I increase my pulse width, I can test further. So I increase my pulse width to say 30 nanoseconds. Now I only see 1 event, 1 big event, but it's good down here. So I'm able to see further. But this is where time comes in really important for time. As you increase your duration, obviously your test time increases. A lot of us are dealing with 864s and 1728s and those types of system fibers. 864, if you're testing an 864 and you add 1 second, just 1 second to each fiber, that's 15 minutes. That's just 15 minutes, 2 seconds, 30 minutes. So it's really impactful. So you really need to determine what the sweet spot is for your settings, right? And the difference between pulse width and duration is where where we need to determine that. Distance is pretty simple. I want to see the end of fiber, and I want to see the noise floor. But for the difference between shorter and long pulse width is, if I want to see 50, 60 miles, I'm going to sacrifice seeing the 2 connectors up front. If I want to see the 2 connectors up front, then I'm going to sacrifice 50 miles. That's one of the issues with an OTDR. You need to shoot a short shot, and ideally an intermediate shot, then a long shot, right? Multiple pulse width, more than just 2. because I need a short shot to look at my office information. I need an intermediate pulse width to look somewhere in the middle, and I need, to scale that as the fiber gets longer and longer. And so you have to determine what you're going to do. So a lot of folks that are running OTDRs are doing a short shot to look at the office information, then doing a long shot to look at the span. It's not uncommon, particularly on backbone systems. And so that's what happens here, right? Is kind of distance versus resolution stuff. And there's two issues that we're going to have here when we manipulate pulse widths and stuff like that, right? There's two things that are going to happen.
Kevin?
Yes.
We actually have a question.
Oh, excellent.
Yeah, somebody asks if they have a really long fiber and need detail, just put long duration and low the pulse.
Yes, absolutely. So in fact, I'm going to show that. So as you increase your duration, you can reduce your pulse width. So you're able to use shorter pulse widths at a longer distance, but there's going to be a diminishing return. You're never going to take a 5 nanosecond pulse width and set it to 5-minute averaging time and expect it to test 100 kilometers. It's never going to happen. That's just not enough power. But if we increase the duration at 5 nanoseconds, we will be able to shoot a little bit further, at that. In fact, I'll show that to you when I actually manipulate those back and forth, because that really is the key. The key takeaway is ideally you want the shortest possible pulse width in a reasonable amount of time to get all the information that you need. And sometimes that means more than one shot, unfortunately, because the two biggest issues that run into that are going to be dead zone and resolution, right? And so dead zone and resolution, these are directly affected by pulse width. And so what is dead zone and resolution? So dead zone is an area of the fiber after a reflection that we're blind from. So when you see that big spike on an OTDR trace, and I'll show it to you when I switch back to the OTDR, that big spike, that gap in between the start of that big spike and the end of that big spike, right? The start of the reflection and, the end of the reflection. This is dead zone. This is the area of the fiber that you have no visibility to. This happens after every reflection. It's like looking into high beams. You look into high beams and you adjust your eyes, you don't see 100 feet of the road. That's dead zone. You're still traveling across that pavement. You're just not knowing what you're hitting as you go across. So we know what the loss looks like going in. We know what the loss looks like coming out. We just don't know what's in here that caused the loss. Was it only one event? Was it only a connector? Or was it a connector and a pigtail splice? Or was it, two connectors? Who knows? This is resolution. So as you increase your pulse width, and keep in mind this table here, there's assumptions being made. I probably should have put a little, thing down here, but this is kind of a good guide that you could use. So let's say that you're doing 100 nanoseconds, which is pretty typical for a metro shot from site to site. So this is about 70-kilometer distance. It has 13 meters of dead zone after the reflection. So that means when this pulse hits this connector for 13 meters, anything within those 13 meters is going to be measured together as one big event.
Kevin?
Right? Yes.
We have another question. Sorry.
Sure, that's fine.
Does it make a difference if the circuit is live?
It does. In that you cannot use 1310 and 1550 on live fiber, because then it'll interrupt traffic. I mean, obviously, well, you're already intrusive into traffic anyways, mostly. But it won't work because the incoming light can damage the OTDR. And most OTDRs, right around neg 26, 25 dBm, you can damage the detector, which is not a whole ton of light. You need to use what we call an in-service OTDR. Something I recommend 1650 nanometers because of XGS PON, which sits at 1577. So you want to have some sort of distance between the two. We have what we call in-service OTDRs that will filter out the operating wavelengths, so it doesn't get into the sensor of the detector of the OTDR, and then test downstream live. So we do have those. We do have those. Now, as far as analyzing the results, it's the same. It's all exactly the same. And then if you increase your pulse width even more, you can start to see, we have 1 or 2 kilometers of dead zone. This is also a good way to measure what length of launch cable you need to use. Because one reason why we have a launch cable, some folks call them dead zone eliminators, because we're eliminating the dead zone from the OTDR. Because where's the first reflection in a test? the OTDR port itself. So if I plug in a 3-meter jumper into an OTDR and I set my pulse width to 50 nanoseconds, I'm going to merge the FDP into my OTDR port on my launch. So the launch of the OTDR is going to go like this and then take off. But we have 6 meters of dead zone here, but we have a 3-meter jumper. So somewhere in here is my FDP, and it's not being measured discretely. So this is where, so after every single reflection, you're blind to it, right? You're blind to, to after every single reflection. Then there's resolution. Resolution is the sampling of the pulse. So this is a great little table. Take a screenshot if you have an opportunity to. This basically shows you what is the speed of light, within a vacuum in space versus within, say, standard fiber. So in space, we're running about 300,000 kilometers per second, right, roughly. As that light enters the atmosphere, it slows down slightly. As it enters water or glass, it changes speed. So we're slowing down pretty considerably. So if you look at the speed of light within glass, you're going from 300,000 kilometers per second to 204,000 kilometers per second. So we slow down fairly significantly, right? This is why hollow core is a big put. Folks are looking at hollow core fiber because hollow core fiber is essentially air. So the signals, the circuit will travel faster in hollow core fiber, thereby reducing the latency and increasing the per second part of bandwidth, right? So that's why there's a big interest in hollow core fiber right now, is just to get that little bit of extra speed. That's why there was a big push for some of these, startup companies years ago to place fiber across the country as straight as possible. Because you place it as straight as possible, you reduce the latency because now you don't have those twists and turns in there, right? And so this makes you the speed of light based on time. So if we have a 10 nanosecond, pulse width, we have about 2 meters of resolution, which means we're measuring 2 meters of the fiber at a time. This doesn't test very far. But if you get up here to where you're getting into, say, like 5 microseconds, which is what we see in ultra long hauls, or sometimes higher than that, I don't like going above that because now we start to lose some tremendous resolution. This is 1 kilometer. So that means if I have a splice here and I have a splice here in my network, and these are a 0.5 kilometer apart, at this pulse width, we're measuring them both as one big event. So 1.2 dB, but this is divided by 2. So this is where resolution comes into place. This is where you gotta, and obviously, if you have a long fiber, there's nothing you can do about that, right? You have to use a longer resolution or a longer pulse width to test further. But by reducing the averaging time, you can make that a little bit better, right? And so, that's one of the things that's going on. And somebody asked, do more of the U.S. Live fiber using the 1650 in service? We're seeing it more and more. So our company internally, for some of our larger standardized customers, we've transitioned a lot of our 1625 to 1650. Just because of the use of XGS PON and 10 gig PON, utilizing things like 1577. So being further away at 1650 for in-service testing has a lot of advantages there. So it is something to look at for sure. It's not for every situation, but that's important to understand. One additional thing to understand is the difference between mode field diameter and core size. This is incredibly important. Mode field diameter is the section of the glass being the cladding in the core that the signal travels through. Because believe it or not, the signal can travel through a little bit of the cladding. And so this is where we get gainers and losers. You can get gainers and losers from core mismatch. So if you're splicing G.652 glass, standard fiber, to say G.655 non-zero fiber, the kind of the long haul fiber, they have different core sizes, so you'll see this. But we're seeing this a lot more with fibers that have the same core size, just different mode field diameters. And where we see that the most, bend insensitive fiber. G.657 glass has similar or the same core size as G.652 or standard fiber. They're both about 8.2, 8.3 microns, depending on the manufacturer. So they have the same core size, but why do we get gainers and losers when we go from bend insensitive to standard? Mode field diameter. Core sizes is just that. It's the size of the core. Mode field diameter, kind of this effervescence thing, is the section of the glass the signal travels through. especially the longer signals like 1550 and into the L band, they travel a little bit more into the cladding. So if you flip this on its side, to the left, I have standard single mode fiber. To the right, I have bend insensitive fiber. Where do we see this transition the most? Going from the office to the outside plant. Going from the outside plant to the CPE location. We see that, right? Drops can be ordered as bend insensitive. Fibers that run from, say, a modular pre-terminated FDP that has that tail that goes out to the field and splices at the outside plant bolt. Inside the building, it's bend insensitive. Outside in the outside plant, it's not. So the core size between these two types of fibers are very similar, about 8.2, 8.3 microns in that range. So there's not a core mismatch. That's why you'll see the specs on these. It'll say G.652 compliant, because it is. But what's different is the mode field diameter. And so when you're going from G.652 standard fiber to bend insensitive fiber, the signal changes the way it travels, within the glass. So you have core mismatch. And what that looks like with an OTDR, if you're going from a larger mode field diameter to a smaller one, and if you look here, the larger one was standard glass. So if you're going from standard glass, let's say outside plant to a drop, you're going to see a gainer going. So this is the drop that's bend insensitive, and this is your outside plant cable. You're going to see a negative loss. The other way, right? So if you have bend insensitive to an outside plant, you might see a big loser. And so this is important to understand. Both of these values are incorrect. This is why you need to do bidirectional testing. This is mismatch, mode field diameter mismatch. And so you need to look at them in both directions and get the A to B and the B to A and average them. You need to do this with every splice and connector anyways, right? This is why they have you do bidirectional, because of issues like this. And so it's important to understand what mode field diameter is and where it happens the most. This is typically where it happens. We are seeing G.657 in OSP glass. To get these large 864s and 1728s, some of the manufacturers have switched to bend insensitive, because the big challenge, was never putting a lot of fibers into a cable. It was putting a lot of fibers into a cable that fit into existing duct structures. We're not going to replace all these duct structures. So they've done a lot with trying to get the fiber smaller and smaller cables. And one thing that they do is they squeeze them pretty tight. And when they do that, having bend insensitive fiber has its advantages in that. But this is just something to understand, when you're out there testing. And so when we're looking at the actual OTDR itself, so let me switch to that now, and to tie it all into the finale here, to make this all make sense. We explained range, pulse width, and duration. We explained why you should use a long and a short wavelength to look for macro bends. But there's a lot of companies that are not doing 1310 anymore with high count fiber, because that's 50% more time. And at 30 seconds per fiber, per wavelength on an 864, that's over 24 hours, maybe 23 hours. So it takes longer to test than it does to splice an 864. So there's companies that are just only doing 1550, knowing that if there's anything wrong with 1550, if 1550 is good, then 1310 is good, right? And 1550 will see more issues than 1310 will in most situations. And so some companies are turning that off entirely. And so I'm going to turn it off in this example here. I think I might actually just turn it back on and go back here. Okay, so range, pulse width, and duration. In the past, I always used auto mode to set up an OTDR. I don't do that near as much anymore, because DWDM OTDRs and DWDM transceivers, if you use a DWDM OTDR in auto mode close to a transceiver like an SFP, say you're at the base of a tower and you shoot up, in auto mode, OTDR manufacturers, we auto range at a very high power, 20 microseconds. So you're shooting out like plus 15 dBm of light for a fraction of a second. Because of the nature of DWDM optics, you can actually blow that transceiver out. So in the past, what I did was I said, hey, choose your duration, go to auto, and then hit start, which is still a good method if you're doing dark fiber and you're doing 1310, 1550, and you're far away from your optics. Because we auto based on duration. The shorter the duration, so I'm going to auto at 5 seconds here. And when I auto at 5 seconds, and my span's fairly short, so it'll probably be similar. Basically, the OTDR is saying, hey, what are the best settings at 5 seconds? And it says, you know what? I like 2.5 kilometers at 30 nanoseconds. Nice and clean. I see the noise floor. I see the end of fiber. So I'm happy with my range, right? And I want the end of my fiber here. Usually I want this 8 to 10 dB above the noise floor. All right, I want to have some nice good separation here. I like the noise floor to be 5 dB or less. This will depend on the quality of your OTDR, of course, and the amount of power you're pushing out. So I'm happy with the distance. This pulse width I'm pretty happy with. I can probably get away with 10 if I increase my duration a bit, right? But I get a nice clean trace in a reasonable amount of time. But 5 seconds is pretty fast. Now, if I were to do this again at, say, 30 seconds and auto it, I might be able to get away with a shorter pulse width. This is where the hot and cold of pulse width and duration go hand in hand, is you need to be able to optimize that. And so as you notice here, I'm at, 3 nanoseconds. So it's saying in 30 seconds with it can get away with a 3 nanosecond pulse, which is really, really good. But if you notice over time, it's starting to get better and better. If this time is ticking away and this is solid flat, then all you're doing is wasting your time. It's not going to get any better, right? Reduce your pulse width because you can get away, or reduce your time, one or the other. So I was able to get away with this at 30 seconds. If I'm testing an 864, the difference between 5 and 30 is tremendous amount of time. But in a maintenance situation, waiting that extra 25 seconds gives me a lot more information, right? Gives me a lot more information. So here's what dead zone looks like. If I select this event number 1 here, and I'll speed this up because I see we're almost out of time here. So I'll select event number 1 here. If I go to the event table, that'll make it easier. There we go. I'm getting latency on my VNC now. I'll zoom into it. This is the end of my launch cable. I highlight. If I go to measure, there's my dead zone. I have 2.8 meters of dead zone, which is very, very low. But if I increase my pulse width to, say, 50 nanoseconds and retest this, I'm going to retest this. See, nice and flat. Now I'm just wasting time after this. I'm going to stop it. I'm going to go to the same location, number 1. I'm going to zoom into it. Now I have a much wider pulse here. If I go to measure, it's now 16 or 17 meters. So it's more. So as I increase my pulse width, obviously with such a short distance, you don't really see, as impactful. But if I were to go in here and set, say, 100 nanoseconds, which is a typical site-to-site shot, I had 7 original events. Now I'm down to 6 because I'm starting to merge information together. Now, there's all kinds of problems with this trace. We have way too much power. These peaks are starting to round off. I don't want to see my peaks starting to round off. I don't like that. And then that's what's happening here, right? And so those are 2 things, that I'm looking for. This is a quick indication that I have a bad setup. Now, if I go back over here to event number 1, my launch, and I zoom into it, we don't see that second event much anymore. We can sort of detect the reflection, but we can't see the loss anymore. So now the loss of the patch panel is 0.5 when before it was a gainer. If I go to the second connector here, there's 1 connector here. See this? 1 connector at 182 meters, 0.3, neg 56. Now imagine if this was, say, 1.2 and neg 30, which is really bad. And you shoot this OTDR trace and go, man, that's in that one colo space. You go in there, you clean this connector, you clean this connector, you clean this connector. Retest and nothing improves. Nothing is improving. You keep cleaning it. The problem is you're in the wrong place. If I were to shoot this with better settings, better resolution, say 5 nanoseconds instead of 100. I didn't adjust the duration because I'm just going to stop it when it's good enough for my purposes. So you see, it's much lower on the scale. It's starting to clean up, and I'm just going to stop it now. This is what I needed. Here's that same event that we had before. Now we have 2 events instead of 1. So before at 100 nanoseconds, we had this big thing. We had this sucker here, right? Now we have 2 distinguished events, and before we were cleaning this connector. When the problem, was this connector, which we didn't see, had high reflection and huge loss. But we didn't see it because it fell within the dead zone. This is where optimizing your trace is important. And this is how you can troubleshoot connectors inside of your site. So if this was the 4 walls of my site here, and I know, this is why it's important to know what you're testing, and I know that I have, X amount of connectors in my site, then, I'm going to say, well, this is my site right here. I have 1, 2, 3, 4 connections in my site. And then this is my OSP vault. And so this is my DMARC. I would go in here, shoot a short pulse width to see what my office looks like. These network equipment manufacturers do not want any high reflection or any high loss within 2.5 kilometers or so of the site. And so this is one way to isolate that. Now I know which connector to clean. I'll go straight to the 3rd connector and clean it, or go to the 4th connector and clean it. Leave the other ones alone. I can go clean those other ones and make them worse and just move my problem from 4 to 2, because I went to 2 and cleaned it first and made it, I didn't do a good job of it. And so this is basically how I set up an OTDR, and a lot of it is just really kind of the interpretation. And so in this day and age, how I do it is I will select a short range, a short pulse width, and I will shoot it in real time. And so instead of using auto, so if I'm testing with, like I say, DWDM OTDR, say I'll start with a short distance and a short pulse width so I don't overpower the receivers. Then I'll increase my pulse width until this flattens out. There it is. Then I'll adjust my duration, my distance to whatever it needs to be. And in this case, we're going to do 2.5. Then I'm going to stop it. Then I'm going to determine how much time I need to spend on this. If I'm doing, say, 12 fibers, I'll do 30 seconds minimum, right? If I'm just doing a couple of fibers, I'll do 45 seconds. If I'm doing maintenance work where I'm trying to find trouble, I'll increase it to 60 seconds. The longer the duration, the more information you get, the better the resolution at the expense of time. I'd rather test 60 seconds and get the 4 events than test 10 seconds and only get 3. If I'm doing high count, then I might reduce the duration as long as I don't affect the quality of my results by merging information. And so that's kind of how I do it. So in this case here, I would say, you know what? I'm happy with 15 seconds. Let me go, 50 nanoseconds is going to be too much for averaging. Then I'll just reduce it down. So I'm going to reduce my pulse width and duration to the point where I get the best absolute results, that I can. And that's pretty much in a nutshell. And so I don't know if we have any more questions here. I'm going to talk really quick about IOLM. Just to cover some of this. The OTDR, you can kind of see range, pulse width, and duration and all that stuff. EXFO does have an advanced tool that gets around a lot of the issues that we see with resolution of a test. So we have a tool called IOLM. So it uses the same OTDR hardware. There's some additional components in there, but there's a lot of algorithms and science. At first I was kind of hesitant, felt kind of Skynet-y to me, being an old school tester, but it's really a great tool, particularly for those folks that want to get kind of first time right testing. The big thing is you just got to make sure that your launch is good and clean. And we talked about how to troubleshoot that. You put in your launch cable length, you select your wavelengths, and I'm going to put a pinch in the fiber here. And you select a configuration, which is basically your start fail, your pass fail stuff, and you hit start. And so once the configuration is selected, once you've nulled out your launch cable and clean all your connectors, really all you do is hit start. There's no distance, time, pulse width. There's different configurations for different types of deployments, like under 20 kilometers, under 10,000 feet, tower, distributed tap, PON architectures, all of that stuff. So in this one here, I'm doing a CRAN 20 kilometer test or under. And so just like that, I get actionable items. I have a bad launch, first of all. I have high reflection on my launch. And I saw that when I was looking at the OTDR trace. I can click on this and it says, you know what? This is a dirty connector. There's a little bit of a pinch there too. It says, this could also be an APC connector. And then if I click over here where I pinched it, it tells me there's pinching in this section. The great thing about IOLM is you'll always see something at 60 feet and see something at 60 miles because it shoots multiple resolutions at multiple acquisitions. The trick is to really to get a good configuration that's ideal for your situation. So I'm going to end it there as far as that portion goes. Now you can export an SOR from IOLM. So under user preference, you can say, I want a Belcore SOR with each save. So that way you can get it, or you can do it after the fact with Fast Reporter. You can also, within the element screen, if you're like me and you like seeing the graph, which I do, because the graph helps me with identifying ghost and visually identifying things. That's just an old habit. So it'll take the IOLM and then give you the graph, the trace graph. So yeah, so there's a lot of power there for that itself. So
Wonderful. Well, thank you, Kevin. I appreciate all the information that you've given out here to the team. Unfortunately, we're out of time. We do have several questions, but unfortunately, maybe we can go ahead and I'll send those questions to you, Kevin, and perhaps you can give me some responses, and I can send it to the attendees here.
yeah, absolutely. It's a lot of information, so I apologize if I didn't get to all the comments. You know, it's hard to look to the left and focus to the front. So, but I
No,
do
no.
appreciate your time.
Yeah, no, thank you so much. So I just want to thank everybody who was able to attend the webinar today, and just want to let everybody know this webinar is being recorded, and we will go ahead and share this information to everybody. So again, on behalf of Kevin, myself, from EXFO, from Electron, thank you so much for attending. Enjoy the rest of your day.
Thank you very much.
Thank you.